So this is video number 2 for Chapter 7, Electricity and Magnetism. Last day we looked at how you can create magnetic fields using currents with either a long straight wire or preferably with a coil of wire called a solenoid. And today we're going to start to look at a 2-day-long process of finding the force that can be caused by a magnetic field on either a moving charge or on a current. They're kind of the same thing, but we'll look at them as two separate stories. We're going to go back and forth a fair bit between just looking at some pictures and thinking about things. I'm going to put this little icon up for just like, hey, throw your pencil down for a second, don't worry about taking any notes. And then a different little picture for when it's time to take some notes. So let's just look at some stuff for a minute. You don't need to take any of this down. I like to start these days now with just a review of what we've seen so far. So after the first day, we've seen that permanent magnets have a north end and a south end, and magnetic field, this human contrived thing to explain forces, comes out of the north end of a magnet, wraps its way around, and then penetrates back into the south end of the magnet. Magnetic fields from steady currents is our next topic that we looked at after we looked at permanent magnets. We said, okay, you can do a long straight wire, and that does make a magnetic field, but it's not very strong. And the equation for how strong it is mu naught I divided by 2 pi r, and r is how far you are away from the wire. The magnetic field circles the wire, and you had to do that right-hand fist grab in order to figure out which direction it was actually circling. Instead of showing it as a 3D circle, just be aware of this. Sometimes people show the 3D circles as X's on one side, that's arrows going in, and dots on another side, that's the magnetic field coming out. So those two pictures are exactly the same thing. Some people prefer to draw it one way and some people prefer to draw it the other. So just do be aware of that. The solenoid is a better way to go, much stronger, cleaner direction magnetic field, much stronger as well. And a couple of equations there, but either way, no matter how you look at it, that center part, N divided by L, or little n, figures out the number of wraps per meter. You still need to do that right-hand grab with your fist in order to figure out the direction of the magnetic field on the inside. And where we're progressing to today is going to be part C. It's going to take us a couple of days, and we're going to take a look at how magnetic fields, either from permanent magnets or from currents and in a solenoid or a wire, can actually create forces on things, on moving charges or on currents. So this is a little picture I'm going to show you when it's time to grab your pen and take some notes. Again, part C is forces on moving charges and currents from B fields. And the first thing to note is that we are going to split this up over 2 days. Today we're just going to take a look at moving charges. You know what happens if a proton or an electron goes flying through a room that's full of magnetic field, and what kind of force should it experience? And then next lesson, we'll take a look at currents. What happens if there's a wire that's got some current on it and it's sitting exposed to a magnetic field? All of those moving electrons behave like moving charges because they are moving charges. They're all going to feel a force, and it's going to shove that wire around. But we're just going to start off with moving charges today, what I've just highlighted there in yellow. Now, we're right back to putting our pencil down again for a second. Let's just take a look back at what we already know from a couple of chapters ago from electric fields and how they can create forces. So no copying for a second. Let's just think about this for a minute. If you have two parallel plates, one charged positively, one charged negatively, that creates an electric field in there. And should you go and put a charge in there, that charge is going to feel a force. That's what the field's warning you about. The field in this direction, in this picture, would be to the right, warning us that if you put protons in there, they're going to get shoved to the right. That Q, I know right now that Q is going to feel a force for sure. The only thing I don't really know is which direction. It might be this way. It might be off to the right. That would be what would happen half the time if I put a positive charge there. And F equals QE would let me figure out how big that force is. The only other thing that can happen is maybe the force goes back the other way. Maybe it's anti-aligned with the electric field if the Q happens to be negative. But that's it. Just those two possibilities right there and there. You might think that the magnetic field story would be just as easy, but it's not. So imagine you have two bar magnets and then you space them out a little bit so that there's a space between them, between the north end of one and the south end of another. And we go and put a little Q in between those two magnet pole ends. So there's definitely a magnetic field, what we just usually call a B field, in between that space, between the north end of one off to the south end of the other. And you might think that that force would be in that direction, or maybe anti-aligned with it if the Q is negative. But life's not that simple, and it turns out from just experimental work, we found that this equation predicts what that force is going to actually look like. It's quite a bit more interesting than just Q times E than we had for electrostatics. There's actually a velocity in there and what's really cool, there's a cross product in there. So we're going to have to do that cross product deal with that right hand crazy shape we did back in chapter 1, that big blue styrofoam hand that was in the classroom, trying to figure out which direction the right hand rule is going to go. And then there's the velocity in there as well. And the fact that the velocity is in there right here tells me that if this cue sits totally motionless, just doesn't move, then the velocity would be 0 and there would be no force on it at all. So this magnetic field, not only does it act in a weird way with cross products, but if the cue sits motionless and doesn't move at all, it's kind of like the magnetic field can't even see it. Kind of reminds me of that scene in Jurassic Park where if the little kids were really, really still, the T-Rex dinosaur couldn't actually see them. It's kind of like that for this little cue. If it doesn't move at all, the magnetic field won't even be able to see it. But if it does move, well, then there's going to be a big force on it. Okay, well, let's start splitting this up. If part C is going to be the section for 2 days, then part 1 is going to be just that first half. Let's look at the force on a moving charge in a B field. Okay, and you can see from my little picture there, it's going to be time to take some notes here again. So we'll scribble some stuff down. Here's the equation again. It's an experimental equation. The physicists have noticed that this equation does a great job predicting what that force will be just based on experience. Okay, it's an experimental equation based on just our experimental evidence. It does have that cross product in there between the velocity of the cue and then the magnetic field that it's in. And I've just labeled the little digits of your right hand, the important first 3. And let's go back and take a look at chapter 1 for a minute. Okay, so we'll go back to pencils down for a second. These were some notes that you took back in chapter 1 when for 1 day we were playing around with cross products. And we said if you were crossing A crossed B in order to find C, then you could actually use your right hand in that orientation there to figure out which way that answer C would be. So what's important to know is the first vector in the cross in the mathematics question, the one before the cross symbol, always has to be your thumb. The one after the cross symbol is the next digit along your hand as you work your way along your right hand. And then the answer is going to be given by the third digit in your hand. Your middle finger will show you which way the answer goes. So let's take a look and see how this electromagnetism story actually works. The first vector before the cross is the v, the velocity. So for this chapter, when you have a charge moving in a magnetic field, your thumb needs to be the velocity. Every single time, your thumb represents the v. The next thing after the cross is the b. That's going to be the pointing finger in your right hand. That will always represent the direction for the magnetic field. And then finally, the answer, that force vector is going to be the third digit. Okay, the middle finger of your hand will represent that force. Okay, what I've denoted there in F. Okay, for force. And then you just have to always make that orientation with your right hand and then just carefully move your whole right hand around, but don't actually start like swizzling your fingers. Keep your fingers in that orientation and just simply move your hand. So in this story back here that we started with, just looking back to it for a minute, if that cue was actually moving away from you into your paper, then the force would be actually up towards the top of your paper. It's completely three-dimensional, which is kind of cool. We're going to practice that here in a minute. Okay, some more stuff just to scribble down. The idea of the cross product is great. Cross products work best when the vectors you're crossing are perpendicular. So I'm just going to say kind of just qualitatively that this creation of force works best if the V and the B are perpendicular. That's what that little upside down T means. If they're not absolutely perpendicular, then we can do our usual cross product game and say, okay, well, just take the size of the V and the size of the B, okay, the size of the two vectors, we'll multiply them together, and then we'll also throw in a sine of the angle. That's how cross products always work for ones that are not quite perpendicular. Be aware of this. It happens half the time. Negative charges, such as electrons, exactly disobey the right-hand rule. Because their Q is negative, the force will be in the exact opposite direction than that big blue styrofoam hand inside the classroom would actually predict. So be careful with that. You can do that right hand gesture, but then when you're done, you have to remember if it's a negative charge story that you have to reverse your answer, and we'll try a few of those out here today. Let's try just 3 right hand rules out, and we'll see if we can actually do this online. So We'll give you a second to copy out these 3 separate questions. We're going to see if we can find the missing vector in each story. And what I need to tell you is that these 3 stories, they represent a charge that's moving, some sort of Q, inside a B field. And I have to tell you this, I'm going to tell you that for all 3 of these stories, the Q is not like an electron. It's actually positive. So think of it as a proton. So in question number 1, the one on the left there, this proton is moving off to your left. Okay, it's moving to the left side of your paper, but the magnetic field is up towards the top of your paper. So now you have to take your right hand and make that orientation, the orientation that looks like this. And when your right hand looks like that, let's get the 2 vectors lined up that we have. Make sure with your right hand you have your thumb pointing off towards the left side of the paper. While your thumb stays pointing to the left, move your hand around until your pointing finger actually points up towards the top of the paper. Okay, so you've got your thumb pointing left, your pointing finger towards the top of the paper, and now look at your middle finger. It should be pointing into the page, penetrating into the page. So if there was a proton moving to your left in a magnetic field that's towards the top of the paper, it will actually get pushed into the paper as it moves. And we can draw that just as an F with a little X like that to show that it's into the page. The next one, we're missing the magnetic field. So we're trying to figure out which way your pointing finger is pointing. Your middle finger is that force finger, and it looks like a dot. It's coming out at you. So move your right hand around in space until your middle finger is pointing at you. And while your middle finger stays pointing at you, roll your hand around that axle until your thumb, the velocity, points to your right. And then look at your pointing finger. It should be pointing towards the top of the page. One final one. Let's see if we can find which way this Q, this positive Q, is moving. You can pick either letter to go first. I'm going to pick the force. So take your force finger, your middle finger of your hand, and have that go away from you into the paper. And while it's going into the paper, twist around that finger until your pointing finger points towards the bottom of the paper. It's a very awkward one to get your hand into that position, but your middle finger needs to point into the paper while your pointing finger points to the bottom of the paper, and your thumb, if you've done it right, should be pointing off to the right. So this charge must be moving that way. So that's half the battle today, is just actually getting that right hand rule to work. And we can practice that online in our online sessions if you want, because it's definitely something that the first few times you try it, it's pretty easy to wrestle with. The other half is to try to figure out the numeric values. So let's try a couple of examples out, and then we'll be done. When we do this, okay, yeah, pencils down here for a second. Be careful with directions. The safest directions are what I'm showing you here on the left. The compass for north, east, south, and west, and then we can talk about out of the page and into the page. Be incredibly careful with the word up. It's no longer clear what that means. Does it mean up towards the top of your note paper, or does it mean up out of the paper into the sky? Sometimes people clarify the difference by saying up and vertically up. Okay, you can, but be super careful with that. I would try just to avoid the words up and down in this chapter, and you'll be much safer. Okay, let's grab our pencil here again, and we'll try a couple of examples. This first one, find the size and the direction of the acceleration of an electron. Okay, it's negative, it's an electron, so it's going to be all backwards. Moving with a really fast velocity there, 2,400 meters per second, 60 degrees north of east in a 1.8 Tesla facing east B field, magnetic field. All right, well, we've got to find size and direction. Let's go for the direction first. So I'm just drawing in those vectors, and when you're doing cross products, unlike adding vectors, it works very well to put the 2 vectors tail to tail. So I'm showing the velocity and the magnetic field both coming out of the same origin, the same point where they begin, and the velocity has to go 60 degrees north of east. Now take your hand in that right hand rule shape, and you can kind of move your thumb like the trigger on a gun. It can relax a little bit. Your thumb has to point in that 2400 direction, while your pointing finger points to the right. And it has to be your right hand, and when you're doing that, you should find that your middle finger points into the page, like an X. So I'd be very tempted to say, oh, okay, yeah, the force and the acceleration that comes with it is going to be into the page. but of course it's an electron, so we'll have to remember that it's the opposite of what that right-hand rule just taught us. It's actually going to be out of the page for an electron. Now, for the size, since the V and the B are not exactly perpendicular, I'm going to go with this plan of the V and the B multiplied together and the Q, and then the sine of the angle, which looks like it's 60 degrees. So the Q, I just grabbed that right off of the formula sheet. There's the Q for an electron. Multiply that by the velocity and the B field size, and then sine of 60. And I have my force. They did ask for acceleration, so I have to go through one more step. I'm going to have to do F equals ma. I'm going to grab the mass of the electron just from the formula sheet as well, and then I can find the acceleration. No point even worrying about the force of gravity. It will definitely be way too small to worry about. So we'll assume that this electromagnetic force is the net force in this story. So there's the size of the acceleration. Now remember, up near the top of the page here, the right-hand rule was saying, oh yeah, into the page. But it was an electron. So I'm going to disobey that order and say, no, it's actually going to be out of the page. So that's going to be what a classic question would look like for us with this particular topic, this force that's equal to QV crossed with B. Now, for the last little bit of the day, just going to do some thinking. Don't have to write anything down on paper. Just going to think about what's going to happen here, kind of foreshadowing some stuff a couple of days down the road. What's going to happen with this proton if it goes flying into a room that has magnetic field going into the paper? And again, you don't need to copy this down for now. We'll just look at it. So you've got B field. All those X's are B field. Apparently it's pretty strong, 1.45 Tesla, penetrating down into your note page. And this proton, if you wish, is about to enter that space. Well, here's what happens. The moment it enters that space, now that F equals QVB starts to apply. And if you take your thumb and point it to the right, while your pointing finger, the B finger, points into the page, your force finger will point up towards the sky. And you might think, oh, okay, it'll just curve a little bit. But it's actually more interesting than that. Because as it starts to curve, then the velocity direction changes. So now in this position, try doing the right-hand rule again. But you have to have your thumb pointing towards the top of your notepaper or towards the top of the screen. And when you do that, you see the force is this way. And so it keeps turning. And it actually does beautiful circular motion. Or maybe I should say half circular motion, because it'll do a half circle by the time it's ready to leave that space, and then it will go shooting out the other direction. If you desire to see a full circle, it's possible to do it, but you'll have to start inside the space. So if you have a way, and we'll see a technique to do this with particle accelerators, where you can begin in that room of magnetic field, then that force will actually make this thing continually go in a circle. It'll just stay contained in there. It's beautiful circular motion. We could do good old net force equals ma. For the A, we could put like V squared over R like we've done before. And for the force, you can put in QVB. And we'll see that that's how the particle accelerator down in Vancouver actually works down at Triumph. And that's where we're going to finish up for our second lesson today.